Hello again, everyone. My name is Rick Frage. I am the sales director at SFTech. With me today is my colleague in the sales, Ilyas Akiki, and Dr. Ahmed Al-Vadi, and also Dr. Girish Naraya, who will be presenting today, who will be the main speaker in the presentation. Um, so today's presentation is basically an introduction to glass fiber polymer. We're going to be covering a little bit about the material, behavior, design guidelines, design examples, and case study. So just a little bit about Dr. Girish, so that you know who will be who will be presenting and sharing his information with you. Dr. Girish, basically, as you can see, I refer to him as doctor. He completed his PhD studies in civil engineering at the University of Sherbrooke in Quebec, under, of course, the supervision of Professor Ibrahim Ben Mukran. And he's basically specialized in, he also did a master's, in earthquake engineering from the Indian Institute of Technology back in Roorkee, India. Before that, he received the University Gold Medal in 2013 for the Best Bachelor's Project from the Veer Surendra Sai University, also in India. Currently, he's actually working with us, and also he's a MITAX Industrial Postdoctoral Fellow at the University of Sherbrooke. His interests include the behavior of concrete structures reinforced with hybrid reinforcement. So basically, when you're reinforcing steel and fiberglass in the same structure, the characterization of FRP bars, structural dynamics, finite element analysis. He's involved in several projects with Canada Research Chair in advanced composite material for civil engineering. For civil structures, sorry. Dr. Girish also has played a pivotal role at SFTech in two different aspects. First, in the pursuit of excellence in material certification. So basically, his extensive involvement spans a multitude of completed and active projects that focus on enhancing the durability and resilience of concrete structures throughout the integration of SFT bars. His contributions also extended to beyond the practical applications. He has imparted his knowledge and insights in numerous conferences and seminars. His presentations, like this one, bridge the gap basically between the practical world and the academic research, and sheds lights on the transformative impact of fiber-reinforced polymer bars on civil engineering. I'd like also to add he has been a very important player from the sales department's perspective, as he participated in a lot of sales meetings where technical questions came up and he answered, instructed the engineers in the client's projects. He also worked on several projects for us, converting and redesigning from steel reinforced concrete to fiberglass, including structural slabs, vertical applications, footings, foundations, and so on. I will leave the mic for him. So Dr. Girish, the mic is yours. Just 1 second before I do that, actually, there's if you have any questions, please don't be shy to ask. There's a Q&A icon at the bottom. Please feel free to use it. If you prefer to speak, there's a raise your hand icon also. We can always turn on your mic if you'd like to ask questions. Also, towards the end, we might be sending you a small survey to rate the presentation and see if you're interested in future presentations. Dr. Girish, the mic is yours.
Yeah. Thank you, Rick, for the brief introduction. So today's topic is the introduction of glass fiber reinforced polymer bar. So So the content of the presentation will be a brief introduction about our company, the projects we have done, the introduction on the fiber reinforced polymer bars, what design guidelines we have till now, few design examples, like basically 2 design example, and a case study showing the cost analysis. And finally, I will conclude the presentation. So about our company, our products are mostly designed in Canada and are manufactured in China by Sandok Safety Industries Co. Limited, which are specialized in manufacturing of fiber reinforced polymer products. So we work with national and international engineering firms. We work with them through the design process and help them with the fiber reinforced polymer design standards, whether they are in Canada or in the United States. So we also focus on the parking facilities, water treatment plants, and retaining walls. And our main focus is on the glass fiber bars and the carbon strap applications. So SFTech FRP bar is made from composite material. The composite materials are generally fiberglass or carbon fiber, and is manufactured by pultrusion process using a mix of recycled fibers and resins. So here you can see a microscopic image which is showing the view of the interface resin and the fiber. So there are 4 different types of fiber used in the FRP reinforced polymer bar. Those are glass, carbon, basalt, and emerite, and their stress strain properties in comparison with the steel bar is shown in this figure. So we can produce different types of FRP products depending on the project requirements. And some of the FRP bars we produce are generally straight bars, spiral, stirrups for transverse reinforcement, bent bar and glass, fiber reinforced polymer shear connectors. And the shear connectors are used in the ICF walls. The glass fiber reinforced polymer bar is used due to its production cost and have better tensile strength compared to other FRP bars. So why should we use aseptic bar instead of the steel bar? So here are some of the advantages of the glass fiber reinforced polymer bar over the steel bar. So it have longer service life because of its corrosion resistance. So therefore, improved durability in harsh environments such as construction near coastal areas in North American cold climate. The FRP bar have better resistance against corrosion compared to the steel bar. The tensile strength of FRP bar is around 2 to 3 times more than that of the steel bar. I'm talking about the glass fiber reinforced polymer bar. If you consider carbon, it have more tensile strength compared to the steel bar. However, however, it is lightweight. It is because of the low density compared to the steel bar, and due to the corrosion resistance, FRP bar are good for the harsh chemical environment, which are in Canada. Because of the cold, we have to put alkaline salt during winter, and it is also neutral to electrical and magnetic disturbance, useful for applications such as airport, military applications, MRI rooms in hospitals. So coming to the second section of this presentation about the fiber reinforced polymer bars. So there are different fiber external surfaces of the fiber reinforced polymer bars are available in the market. So from left to right, you can go the first bar is the sand coated and helical wrap, and the second is only the helical wrap, and the third one is the ribbed bar, fourth is the sand coated, fifth one is the helically grouped, and the last one is similar to the first one with helical wrap as shown in the bar. So different available FRP bar shapes for the reinforced concrete structures are straight bars, bent bars, and spirals. So the Canadian and American material specifications such as CSA S807, ASTM D7957, and D8505 set some minimum qualification and quality control properties for the GFRP bars. So we'll go through them. Same as the steel bars, table one shows the CSA S807, and table 3 in ASTM D7957 and D8505 provide GFRP bar diameter and area range for measure values for any GFRP bar external surfaces. So this figure shows a stress strain profile of the GFRP bar, and we can see here The GFRP bar have higher tensile strength than the steel bar, but they are less steep than steel bar. So therefore, the FRP reinforced concrete members can have more deflection compared to the steel reinforced concrete members. FRP bars have high strength in fiber direction due to the anisotropic behavior. The stress-strain behavior of FRP bars are linearly elastic up to failure, so therefore they doesn't provide any ductility. However, this can be overcome by providing hybrid reinforcement of steel and fiber reinforced polymer bar. The current research is going on to implement a hybrid reinforcement for the new ACI 440 design code. Since the glass fiber reinforced polymer bar doesn't have any yield point, the guaranteed steel tensile strength of GFRP bars vary between 550 to 1350 megapascal. So the guaranteed tensile strength is founded by the by subtracting 3 times the standard deviation from the average tensile strength. The GFRP bar have lower average elastic modulus, vary between 50 to 45 to 60 gigapascal, and the guaranteed ultimate tensile strength of GFRP bars vary between 1.2 to 2.5%. So generally, this variation depends on the amount of fiber and resin content. The design tensile strength of the GFRP bar are calculated by multiplying a resistance factor, and which is equal to 0.75 in CSA S806. So this value is generally introduced in the 2012, and the CSA S806 has not been updated. It's only reapproved until 2009. So in the next provisions, in the next updation of the CSA S806, the value will be increased to 0.85. And the latest ACI 440.11 design code uses an environmental reduction factor, which is equal to 0.85, which is based on the research paper published in 2020. So the thermoset behavior is characterized by the glass transition temperature as shown in this figure. The tensile compressive and shear properties of the resin decreases when the temperature approaches glass transition temperature. So a glass transition temperature of 100 degrees Celsius is required for vinyl ester, typically used in glass fiber reinforced polymer bar, and lower glass transition temperature are generally result of the moisture absorption. The physical characterization of the FRP bar are done through a series of experimental tests. The important test, like fiber content, is to know the fiber mass content of the FRP bar, and the major cross-section area and the water absorption of the FRP bars are provided. So the details of the tests, the details of this test can be found out in the ACM standard provided here. For SFTech glass fiber reinforced polymer bar number 4, which is tabulated here, the major physical properties satisfy all the testing guidelines. The water absorption is found out in 24 hours and at saturation. So the water absorption at saturation was generally calculated after the 3 week. The tensile properties of the GFRP specimen were tested in accordance with ASTM D7205 or CSA S806. The test specimen was prepared by installation of steel tube on both sides of the FRP bar using expensive cement. The tests were performed under Baldwin testing machine, and the test load was applied until the failure occurred. So according to the ASTM D7957 or D8505, the guaranteed tensile strength was calculated by subtracting 3 times standard deviation from the average tensile strength from the test. And while CSA S807 recommended use specified tensile strength found out by multiplying average value with a factor FT. And this factor is calculated by the following equation, where V is the coefficient of variation and N is the total number of samples. The transverse shear strength and the horizontal shear strength of the GFRP bar were tested using MTS universal testing machine. The displacement rate was selected to produce failure within 1 to 10 minutes, and the force was applied uniformly without subjecting the specimen to impact. Pull-out tests are performed to measure the bond strength between the reinforcing bar and the concrete. The GFRP bars were embedded in the concrete blocks, and the concrete batch have a compressive strength of 35 megapixel. The pull-out test was conducted using a Baldwin testing machine as shown in this figure. So for SFTech GFRP bar number 4, the major mechanical properties satisfy all the testing specification, and the CSA S807 classify GFRP bars into three categories based on the modulus of elasticity. So the tested bar generally came under the grade 3 with more than 60 gigapascal modulus of elasticity. And ASTM D8505 is the recently introduced specification to account for the GFRP of basalt fiber-reinforced polymer bar with more than 60 gigapascal of 60 gigapascal of modulus of elasticity. The method used to access and validate the durability of FRP bars are accelerate aging or alkaline test. So in this case, we immerse the FRP bar in water with alkaline salt under high temperature. The temperature is usually 60 degrees Celsius. And this process is fast process, and test is conducted after 3 months of immersion or exposure to the alkaline salt. And in the second process is the extraction of samples from the real structure. And this is slow process, and the test is conducted after 15 years of structure service. So the durability of GFRP reinforcement in concrete was assessed by excavating core from different bridges located across the United States. And the result from the study indicated a reduction in tensile strength of 2.13% over a period of 17 years. That would correspond to a drop in strength of 12.5% over a period of 100 years, with degradation rate assumed to be linear. So in the next section, we'll talk about the design guidelines. So the currently available design standard for design and construction of building structures with FRP bars are ACI 440.11 and CSA S806. So where the ACI 440 only recommended only consider GFRP bars, and for the highway bridge design, the available design standards are ASTO, which is the 2018 edition, and CSA S6, and the chapter 16 of the CSA S6 consider the FRP bar. The assumption made in the design of FRP reinforced concrete structure, according to the both CSA S806 and ACI 440 are the plane section, the plane section before loading remain plane after loading, which means that the strain developed in concrete is proportional to the strain developed in the FRP bar. So, and the assumed maximum allowable concrete compressive strength is 3000 microstrand according to ACI and 3500 microstrand according to CSA S806. The rupture strength of the concrete is very low and should be ignored in the design. And the considered tensile behavior of the FRP reinforcement is linearly elastic until the failure. And a perfect bond exists between concrete and FRP bar. So there are three different failure modes in the flexural members: compression control, tension control, and balance failure. So we'll go through them one by one. So the compression control design of the flexural member will cause the concrete crushing prior to the FRP rupture. So therefore here the section can be called as over-reinforced section, or stress in the concrete is non-linear. In the tension control design, the FRP bar fail first in the flexural member, and the stress developed in concrete may be linear or non-linear, and the section is under reinforced. And the simultaneous concrete crushing and FRP rupture occur in case of the balance failure. So the general consideration for the design of GFRP reinforced concrete flexural members are: The flexural capacity of an FRP reinforced concrete member depend on either tension or compression mode of failure, that is FRP rupture or the concrete crushing. Over-reinforced or under-reinforced section are acceptable for the design. However, it should meet the strength and serviceability criteria. FRP reinforcement is brittle, but they provides warning in terms of large member deflection. The flexural behavior of FRP reinforced concrete member is not ductile, so therefore resistance factor are used. Small resistance factors are used for FRP reinforcement. The following serviceability criteria is required. The stress under sustained and cyclic loading should be checked to avoid creep rupture and fatigue rupture. The substitutions of FRP bar for steel bar on an equal area basis would result in large deflection and wider crack width. The design is governed by deflection under service load and crack control. The excessive crack is undesirable for aesthetic and other reasons, and deflection should be within the acceptable limit to support such as non-structural elements. Over-reinforced or compression control section typically satisfy the serviceability limit for the FRP reinforced concrete section. So bond coefficient account for the degree of bond between the FRP bar and the surrounding concrete in ACI and CSA design standards. So if the bond coefficient is lesser than 1, it is found to be better than steel. And if the bond coefficient generally depend on the external surface of the FRP bar, and it generally varies between 0.7 to 1.2. And according to ACI 440, it is taken as 1.2. Since FRP bars are corrosion resistance, therefore wider crack width are as compared to the steel reinforced concrete members can be tolerated. So according to ACI codes, the maximum crack width for GFRP bar is around 0.71 millimeter. So now coming to the first design example, which is the design of the fiber reinforced polymer reinforced concrete flat slab. It is a prototype of a parking garage flat slab, and the thickness of the slab is 200 millimeter, and all columns measures 300 by 300 millimeter, and the concrete compressive strength is 40 megapascal. So the problem statements are, I will show how to design the flat slab for flexure, and second, checking the punching at the interior column C8. The first step in flexural design is to calculate the design load. The load is specified in the National Building Code of Canada, and we are calculating the service load and then ultimate load. So that the dead load is simply the weight of the concrete plus the partitions, and the weight of the concrete is equal to 24 kilonewton per square meter multiplied by the thickness of the slab, which is 200 millimeter. And according to NBCC, the partitions in parking garage is equal to 1. So we have a dead load of 5.8 kilonewton per square meter. The live load is taken as 2.4 kilonewton per square meter in accordance with NBCC for parking garage. So finally, we have the service load, which is sum of dead load and live load, and is equal to 8.2 kilonewton per square meter. The ultimate load is the maximum either 1.4 times dead load or 1.25 times dead load plus 1.5 times live load. The second provides the maximum value of 10.85 kilonewton per square meter, and which will be going to be the ultimate factor load for the present case. The second step in the flexural design is to estimate the straining action on the floor as the negative or positive moment and shear forces. So now we'll consider that we have the value of the factor moment from analysis. So the next step will be estimate the amount of FRP bars, and all sections are checked to be designed as compression control as per Canadian Design Code CSA S806. The over-reinforced section means that the provided reinforcement is greater than the balanced reinforcement. So now we have resistance factor from this equation and the factor moment from the analysis, and we compare the resistance moment with the factor moment, and the resistance moment should be 1.5 times greater than the factor moment. And if we design following this step, we get the flexural reinforcement ratio of 1%. Further, the design should also satisfy the minimum reinforcement, which is equal to 400 times the modulus of elasticity of FRP bar by gross cross-section area, and this term should be greater than 0.0025 times the gross cross-sectional area. To have a good structural design with FRP reinforcement, the serviceability limit should be checked in such a structure, and the modulus of elasticity of FRP bar is lower than modulus of elasticity of steel bar. So therefore, higher the strength of FRP will not be fully utilized in reinforced concrete structure for the over-reinforced section. Hence, the design is to control the crack width and deflection. The serviceability limit state can be checked using two steps. The first check is for the maximum stress under service load using the following equation. And the code allowed stress under service should be lower than or equal to 25% of the ultimate stress of the FRP bar. And since we know the maximum stress in FRP bar under service load and the modulus of elasticity of the FRP bar, we can get the ultimate strain under the service condition. And when the maximum strain in FRP bar under service load exceed 0.0015, the crack width parameter Z should be verified. So the crack width parameter Z as per CSA S806 could be checked using this equation, and the value of the Z should be less than 45,000 Newton per millimeter for interior exposure and 38,000 Newton per millimeter for exterior exposure. And in parking flat RC slab, it should satisfy the 38,000 Newton per millimeter criteria. So we did the required check for serviceability. Now let's do it for the punching shear at the interior C8 C8 using Canadian standard CSA S806. The cross section of the column is 300 by 300 millimeter, and effective depth of the column is 160 millimeter, and the ultimate factor load is 10.85 kilonewton per square meter. So the first thing we need to find the critical shear area. The critical shear area is the distance d/2 from all faces of the column, and we know that the column cross section is 300 by 300. So the side length of the critical area will be C plus D, and which is equal to 460 millimeter. Now we need to find the tributary area, and the shaded part is the tributary area, which is the area of the surrounding slab minus the critical shear area, and is equal to 24.8 square meter. The ultimate punching shear force is the factor load multiplied by the tributary area, which is equal to 269 kilonewton. And before calculating the punching shear stress, we need to calculate the punching shear parameter, which is equal to 4 times the side length of the critical zone, and which the critical zone is the 460 by 460 millimeter, and the 4 times the 460 millimeter is 1840 millimeter. The ultimate punching shear stress is the ratio of ultimate factor shear force divided by punching shear parameter and the effective depth of the slab, and is equal to 0.91 megapascal. So as we calculated before, the ultimate factor shear stress is 0.91 megapascal, and the allowable punching shear is the list of these three equations according to the Canadian standard CSA S806. And the variable in the equations are S, which is the column location factor, and is 4 for interior column, 3 for the edge column, and 2 for the corner columns. So for the present case, the alpha S is equal to 4, and beta C is the ratio between the long side to the short side of the column and is equal to 1. And EF is the modulus of elasticity and is equal to 65 gigapascal. Rho F is the reinforcement ratio from design, and lambda is the factor to account for the concrete density. And for the normal strength concrete, lambda is equal to 1. And phi C is the resistance factor for concrete. We already know the compressive strength of the concrete and effective depth of the slab. So substituting the value in this equation, we get the least value of 1.08 megapixel. So by comparing the ultimate factor shear stress with the allowable punching shear stress, the ultimate factor punching shear stress is lower than the allowable value. So our structure is safe, and therefore there is no need for transverse shear reinforcement. So coming to the next design problem, which is the GFRP reinforced concrete retaining wall. So this is the simple example of a cantilever retaining wall, which is a rigid wall used for supporting soil laterally so that it can be retained at different level on the two sides. So the current drawing show a cantilever retaining wall designed with steel bars. So all the sections which have shown is a steel bar design, and we are going to convert it to the GFRP bar. So from this example, we'll learn that how we are going to convert a steel bar design to a GFRP bar design. So our problem statement are, so we have to redesign the section using the SFT-Tech GFRP bar. And finally, we'll compare both steel and GFRP reinforced concrete retaining wall. So the available data, we have the available data for the concrete, steel, and aseptic GFRP bars. And we need to calculate the load, which include both lateral loads as well as the vertical loads. And we have to check, and in the second step, we have to check for the stability, which is including overturning moment, sliding, and the soil stresses. And suppose we have because it is a steel, we are converting a steel reinforced retaining wall to GFRP reinforced retaining wall. We assume that these checks has already been done. And now we will analyze the retaining wall, and the factor moment is considered equal to the ultimate capacity of the steel reinforced concrete retaining wall. So for equilibrium, we can get the depth of neutral axis C and just check the failure conditions using the strain distribution, which is subject to tension failure. So then the moment for each section was calculated using this equation, and the moment capacity of each section along the provided steel area are listed in this table. Though coming to the design of the GFRP reinforced concrete retaining wall, reinforcement ratio is calculated as the area of the FRP bar provided for the each section, considering the same area as of the steel bar. And here for the calculation of the reinforcement ratio, here D is the effective depth as given in this table for each of the section. So now we will only consider section 1 for the design, and the design for the rest of the section will be same. Here for the design, we have to apply a reduction factor, and in case of GFRP reinforced concrete, we have to apply different reduction factor depending upon the tension failure or compression failure. So if it is if our reinforcement is requirement is greater than or equal to 1.4 times the balance reinforcement ratio, then it is a compression failure, and our reduction factor is 0.65. And for tension failure, the reduction factor is 0.55. And for the design tensile strength of the different size of aseptic GFRP bar can be found out by multiplying 0.85, which is the environmental factor according to ACI 440.11. The design flexural strength of the section 1 of the stem was calculated by assuming 1 meter wide, and it was found that the reinforcement ratio was lower than the balanced reinforcement ratio. So the section is designed as a tension control section, and the provided reinforcement was checked with the minimum uh, provided reinforcement was checked with the minimum reinforcement because the tension because it was a tension control section. And the design flexural strength calculation is done for section 2 to show how the moment capacity is calculated for compression control section, where the provided reinforcement ratio is greater than 1.4 times the balanced reinforcement ratio. And so we have considered a reduction factor of 0.65. The stress in the FRP bar is calculated using this equation and is equal to 658 megapascal, and which is lower than the ultimate ultimate tensile strength of the GFRP bar. And the nominal and the factored and the design flexural strength is calculated using this equation, where A is the depth of the rectangular concrete stress block, and the minimum, if you see here, the minimum reinforcement ratio, if you see here, the factor, the design flexural strength is greater than the what we require, 433 kilonewton meter, which is greater than the 427. And here the minimum reinforcement doesn't apply because the section is compression control. So following the similar process, the design strength for rest of the section was calculated, and the minimum, and if you see here, for section 3 and section 4, the minimum reinforcement is greater than the provided reinforcement. So we'll provide a minimum reinforcement for section 3 and section 5. So as I mentioned before, for GFRP section, we need to check for serviceability limit. So we apply these checks on the cantilever retaining wall. So we need to check the service level stress in FRP bars. So in this equation, MS is the service moment, and NF is the modular ratio of the elastic modulus of GFRP bars to concrete. The factor K is calculated using this equation for a transform section, and ICR is the cracked moment of inertia. So for section 1 of the retaining wall, the service level stress was around 261 megapascal, which should be lower than the GFRP stress calculated using this equation, the equation to 24.3.2.2. And in this case, DC is the effective depth, 58 millimeter, and beta C is the coefficient. Beta C is a coefficient which is equal to 1.12, and the value here is 277 megapascal, which is greater than the stress level in the service level stress in the FRP bar. So we also need to calculate the bar spacing using these two equations, and we found that the bar spacing is less than what we provided. We provided 150 millimeter, but for the serviceability requirement, the requirement is 126.4 millimeter. So we will reduce our spacing to 125 millimeter. So following the similar process, we'll check the serviceability for rest of the section. And here in this table, I have provided the stress at the service level for all the section and what is the value of F all comparing to F all, and what spacing we required. And I have changed all the provided reinforcement according to the SMAX. So in step 6, we are going to find the longitudinal shrinkage reinforcement. In addition to provide the main reinforcement with FRP bar, so another reinforcement should be provided to control the shrinkage and temperature crack. So according to the ACI 440.11 clause 24.4.3.2, the shrinkage reinforcement can be calculated using 140 divided by elastic modulus of the GFRP bar, and this value is equal to 0.23%. And it should the maximum spacing should be limited to minimum of 300 millimeter or 3 times the thickness of the wall. So based on this criteria, the calculated longitudinal reinforcement are provided in this table, and all the provided GFRP reinforcement details is shown in this drawing. So finally, we'll compare the steel and the GFRP bar for the cantilever retaining wall. And it was observed that the required GFRP bar was more than the steel bar because of the serviceability limit. So if it's, however, if you see the overall cost can be reduced, which will be the discussion about the next part of the presentation. So here I will talk about a case study showing a parking garage slab. So here is a complete parking garage project for which we will see a cost analysis that compares steel with the FRP bar. And the following photos are taken before the restoration. We can see the damage of the steel bars here, steel bars here, damage to the steel reinforced concrete slab in this photo. So these photos are taken during the GFRP reinforcement caging process. The caging process, you can see here, the caging process is almost similar to the steel bar caging. This photo show the GFRP reinforced concrete slab after restoration, and it is in service since 2011. So the project, we are discussing the project. It is a collaboration project between University of Sherbrooke and the City of Quebec. And if you look here, the total cost, if we have used the steel reinforcement, the total cost will be around $831,400. And when we are using the GFRP bar, the total cost come around $794,450. So that is around a saving of $37,000 by building with FRP bar. So although the product they used to reinforce the concrete was twice the price of the steel, they saved money by avoiding waterproofing and installing asphalt, which is not necessary when we are using FRP reinforcement. So the parking garage project was not with us, and it was a very old case study. And the question is now is what is the price of aseptic bar compared to steel bar? So our bars are normally less expensive than the steel, but how does that affect the total cost of a project? Well, there is a actual project here. We work on with the client to help them convert steel to FRP bar. The building is a hotel where the client consider FRP in seven slabs of this building. So the first slab is the most important and the largest, and divided into two parts. The first part is where the reception will be installed, and the second part where there will be a garage, and the part where we can have more saving, and this part is around 937 square meter. So this table present the financial numbers, and we see apart from the slab at level 1, the amount of reinforcement is more or less the same. This is because, as we know well, the amount of RP reinforcement is in each slab is normally greater than the steel because of the serviceability limit, and the steel reinforcement total is around $126,912, and whereas for the steel it is $130,500. But however, the customer can save by waterproofing and asphalt because those are not required for the GFRP reinforcement. So there was a immediate saving of $40,000. That is around 23% of the reinforcement cost. So, however, the number doesn't consider the order potential or future saving. So there are costs of transporting the steel to the site, and these costs are generally higher because steel is 4 times heavier than the FRP bar. The same fact affect the labor cost at the construction site. If a worker carry 5 bars of steel bar per trip, he will be able to carry 15 to 20 bars of FRP per trips, and this translate to saving of almost 25% on the labor cost. And finally, long-term saving for buildings owners and operators. because with FRP reinforcement, there is a less maintenance and concrete restoration work. So here are some of the selected field application of the SFTech FRP bar we have already done in Canada. So GFRP reinforced concrete waffle flooring slab designed with the SFTech glass fiber reinforced polymer bar, which was built in Halifax, Nova Scotia. The FRP bar can be also used for slab on grades. It is a non-structural slab. It is a one-to-one replacement and saved a lot of money compared to steel bar in terms of labor and transportation. So another project shows the cast on site precast sandwich panel, and they have used our glass FRP bars in their project as reinforcement. And in the right is a retaining wall built for the city of Montreal. The retaining wall is designed to dump snow with de-icing salt during the winter. So they built this retaining wall with SFTech glass fiber reinforced polymer bar, which provide resistance against the chemicals used in the de-icing salt. So in conclusion, so due to the corrosion resistance, generally which is more prevalent in the North America, the FRP bar could be used in structural concrete to improve the service life of the structure. The Canadian and American material specification as well as the design standard are available. The flexural capacity of the fiber reinforced polymer reinforced concrete member depend on the FRP rupture or the concrete crushing failure modes. Therefore, either under reinforced or over reinforced section can be used to design the FRP reinforced concrete members. The serviceability requirement such as cracking and deflection govern the design, and the allowable stress under static and cyclic loading must be checked to avoid any creep rupture and fatigue rupture. So the presented case studies have shown potential savings with FRP bars. The transportation labor cost reduced due to the lighter weight of the FRP bars and due to the corrosion resistance. The FRP bars provide better service life with which indicate long-term saving. So if you want to further learn about the FRP bar, there is a workshop you can consider in Toronto on August 8 to 9. So this workshop is jointly organized by Professor Brahim Bemokran, Professor Antonio Nani, who is the current ACI president, and Stephen Nolan. He's with the FDOT, Florida Department of Transportation. So in this workshop, speakers from industry and academia will present their experience with FRP bars and the current research going on the FRP bars for concrete structures. Thank you for your attention.
Thank you again, everyone. Thank you, Dr. Girish, for the presentation. I hope everybody enjoyed it, and we look forward to hear from you soon. Have a great day.